So now moving ahead with the matrix operations we are doing. So we move on to the matrix decompositions. So basically when we are focusing on solving the linear equations using the matrices, so first of all we learned how to solve the linear equations using the Gaussian elimination method. Then we have the matrix decomposition methods which are very popular and which are very much useful in the machine learning. These matrix decomposition methods, they are also called as the matrix factorization methods, because here what we are trying to do is, see, we have seen that when we have small number of variables, it is easy to solve the linear equations. But when we have large number of variables, the task becomes very difficult. So in that case, we say in engineering, what we are supposed to do is we are supposed to simplify the complex tasks, so provide the simple solutions. So here also what we do in the decomposition or factorization, we are trying to break down the complex matrix into the simpler matrix, so that we are able to get the solutions easily and faster. So these are the decomposition methods that we are going to discuss. We are going to study two decomposition methods. Your LU decomposition, you can go through yourself as you have already studied in your 12th class. That is, L is for lower triangular and U is for upper triangular. So what do? You decompose your matrix. Let us say A is a matrix of any dimensions, let us say 3 by 3 dimensions. Then you decompose that matrix into L and U, and then you find the product of that in order to get the solution for the linear equation. Now, then we have, see, why we are focusing on the Cholesky decomposition, or you can say the singular value decomposition, because in machine learning, these are the two matrix factorization methods which we use. Like your Cholesky decomposition, we are using in the linear regressions. Your SVD, that is singular valued decomposition, it is used in the principal component analysis. When you will be studying in the further classes, we will be studying, will be focusing on, you can say, the principal component analysis for dimension reduction. Then you will understand whatever steps we are taking in the PCA, all these have been covered in the linear algebra. So based on these concepts, we see, we pick up one concept of linear algebra, then after that again another step of linear algebra. So we are moving, considering all those steps that we studied in the linear algebra one after the another, and we apply all those methods that we learn in order to reduce the number of dimensions that we have in the data set. So we move on, we start with the Cholesky decompositions. So what is Cholesky decomposition? So here we say every symmetric positive definite matrix M. So that means this is the prerequisite for a Cholesky decomposition, that the matrix that you have taken, so that is positive definite and that is symmetric. So only that can be converted into the, you can say, so you can say if you have a matrix that is positive definite and symmetric, only that matrix, only on that matrix we can apply the Cholesky decomposition. So you can say from the very beginning, if you come across a matrix and you find out whether it is symmetric and positive definite, only then you say that whether we can apply. So first condition that you have to check is whether this particular matrix that you have received, that is suitable for this kind of decomposition or not. So the first thing that you have to check it, if it is suitable for decomposition, only then you apply the decomposition. Otherwise, all your efforts will be wasted. So what do we do when we have a matrix that is symmetric and positive definite, that can be composed into a product of unique lower triangular matrix that we call is at L, and its transpose that we signify, that we write is as LT. So A is a matrix, we convert that matrix into its lower triangular matrix and its transpose. So when we take that particular product of this, so you can say, first you see the symmetric, a square matrix A of size n by n is said to be symmetric if Aij is equal to Aj. That means transpose of A is equal to A. That means whether you see convert the rows to the columns or columns to the rows, we get the same matrix as you see in this particular example. So when we have 1 3 minus 2, and in the see first column and first row they are same. Similarly, you see all the columns, see second column, second row are same, third column and third row are same, fourth column and fourth row are same. So if you take the transpose, so when we have taken the transpose of A, both the matrices are same. So that means we have checked the condition, this matrix that we have received, this is a symmetric matrix. Now, a matrix is positive, definite if it is symmetric and all its pivots are positive. So here you see, when we see its pivots. So let us say you have this A matrix and we convert this into the row echelon form. When we convert into row echelon form, in that case you see, or you can say when we convert it into the lower triangular form, all its pivots are positive. So what are pivots? They are the first non-zero entries in each row, as we have studied in the row echelon form. So they are pivots are the first non-zero entry that is there in every row, that is called as pivot. So first condition was symmetric, that we check if the transpose of A is equal to A, that means it is symmetric. And how do we check whether it is positive definite or not? We check this condition by finding out the pivots. If all the pivots are the you can say they are positive, then we say the matrix is satisfying both the conditions, so we can apply the Cholesky decomposition over that. So you may get this kind of questions also, analytical questions. Looking at just the matrix, you tell whether which kind of decompositions can be applied on this matrix. We can apply LU decomposition, we can apply Cholesky decomposition, or we can apply SVD decomposition, or all the decompositions, right? So we have to understand in the you have to do certain calculations and find out what are the prerequisites which will determine whether a particular kind of decomposition or factorization that can be applied on this matrix or not. Moving ahead now, how do we apply that Cholesky decomposition? So we said that what do we do for applying this Cholesky decomposition? We convert our matrix into two parts, that and we take the dot product of that. So one is the lower triangular matrix and another is the transpose of that particular matrix. So by doing this, what we have, just see this example where we have a matrix. This is the generic form that is being taken over here. So here we have taken a matrix with all the cell values, or you can say all the elements of this particular matrix. Then when we convert this particular matrix, let us say we have converted this into the lower triangular matrix, and second matrix, see L is the lower triangular matrix, and the second matrix that we have taken is the transpose of this particular matrix. And then we take the dot product of that. So here you can see this is the dot product of the two matrices. One is a lower triangular and another is the transpose of that. So this is what the final matrix we get. So how do we apply the decompositions over here? So finding out the final values for the decomposition, we have two formulas. So in general, most of the time, see the formula for computing the diagonal elements. Yeah, we use the, you can say where the, you can say L11, L22, L33. So for computing all those values where the we have the same rows or column value, that means they are the diagonal elements. So computing the diagonal elements, what do? We use this particular formula where we have AKK, that means the initial value that is there in the matrix. Let us say we are computing L11. So K is equal to 1. So we have L11. So computing the first value for this matrix, we have AKK, that is A11, because K is equal to 1 we are taking, and then subtracting J is equal to 1 to K minus 1, and we take the summation of that. So L square Kj, K is equal to 1 and J is equal to 1 to K minus 1. So here 1 is equal to 0, K is equal to 0. So J varies from 1 to 0, so nothing. So that means it will be equal to under root of AKK for the first value. So we will be taking the under root of A11. Then the elements which are below the diagonal element, that means Lik, where I is greater than K. Then these elements are computed using this another formula, that is Lik. So this is equal to 1 by Lkk, Aik minus summation of J is equal to 1 to K minus 1 Lij and Lkj. So we'll do this one example with this so that it becomes easier for you to compute these values. So let us move to the one example and understand how we are computing the values. So let us assume that A is a given matrix, 3 by 3 matrix that we are given. Then we have to express this matrix in the form of lower triangular and dot product of the lower triangular matrix of A with its transpose. Now, how to compute the elements of L using these two formulas? See here, you have both the options that how we are computing that. So, using these formulas, we are computing all the values. Here you see the first value, that is L11. Here it is under root of A11, as we see saw in the, because L11 that gives the this formula, j is equal to 1 to 1 minus 0. So nothing will come in the second part. We will simply have akk. So here A11 is equal to under root of 25. That gives us 5. Similarly, we compute L22. L22 here you see under root of A22. A22 is 18. Then L2 L21 whole square. So what is the value of L21 whole square? That is, we are computed using this particular formula, Lij and Lkj. So you just take the values over here and just try to compute this value. Are you, just take out your notebooks and then see, for L31 we are taking L11 because L31 is not a diagonal value, it is below the diagonal. So for all those elements, see, we have to see the value of k, and we have to see whether we are computing the values for the diagonal elements or the non-diagonal elements which are below that particular diagonal. So accordingly the formula will change. So here we have taken L31 is equal to 1 by L11. So here LKK A31 is equal to 1 by 5 into minus 5 is equal to minus 1. So 1 by L11 we have taken it from here. So we are using the preceding values. So we have to compute these values in sequence so that we can use the previous values which are there in the row or column for the succeeding formulas and use to compute the, you can say, the values in the lower columns or the rows. So similarly, after computing, see, after computing this, see, we are able to get L is equal to 500. So we are getting the lower triangular. See, we have to compute only the lower triangular matrix. Only those values we have to compute. Then we take the transpose of this, and then we say the A is represented using these two dot product of these two lower triangular and the transpose of that matrix. After computing this, see, we are talking about solving the linear equations using the Cholesky decomposition method. So now that means we have understood how we are decomposing the matrix. So the factor of A, because we said it is decomposition or factorization, we call it. So the factor A as A is equal to L into L transpose. So now we say, see, when we do the substitution, A is equal to, we represent any equation using AX is equal to B, right? So here then we are just replacing A because A is equal to L transpose. Substituting the value of A over here, we get L transpose X is equal to B. Now if we assume, let us say, we assume that L transpose T of X is equal to Y. So finally we get L of Y is equal to B. Now let us solve. Again we have reached to the simple equations where we have the new formula. So Ly is equal to B using the forward substitution by getting Y, and L transpose T of X using the backward substitution for getting the value of X. So first of all we will compute the value of Y, and then using that value of Y we will be computing the value of X, which is the final value that we have to find out. So let us assume the same example. We have just converted that into the equations. So here we have again that same A matrix that we have taken in this particular example. This is same. And now these are the linear equations that we have. So using these linear equations, we see, so what we have, Ax is equal to B. Now we have seen that Ax is equal to B. A is equal to, we said that we can represent A using the dot product of these two lower triangular matrices. So that means A is equal to these two matrices that we have computed using the dot product of these two matrices. right? So what we have is 5 0 0. So this is the same matrix, again the same substitution that we have seen previously. So now what we are writing is 5 0 0 3 3 1, the same matrix that we are using over here. So this L is equal to this, L transpose T of this is equal to, so we are writing Ly is equal to B. So represent that equation. What is L? L is this particular one matrix that we have, the first matrix we have picked. Then Y is Y1, Y2, Y3, because we are representing the equations using this, and this is equal to the values of these linear equations. Now from simply looking at these, so the task becomes simpler. So y1 is equal to 5. We can simply see over here 5y is equal to 35. So we can compute the value of y is equal to 7. Then we take 3y1 plus 3y2, 3y2 because the next is 0. So 3y1 plus 3y2 is equal to 33. We know the value of y1 is equal to 7 we have computed. So from the second, what do? Put the value of y1 as 7. Then 3y2 is equal to 33 minus 21 is equal to 12. So y2 is equal to 4. Then putting the values in the third equation where we have minus y1 plus y2 plus 3y3 is equal to 6. So we have y1 is equal to 7, we have y2 is equal to 4. So minus 7 plus 4, you can say, that gives us minus 3. Then minus 3 plus 3y3 is equal to 6. So from 3 we are putting just, substituting, forward substitution we are doing. So we have y3 is equal to 3. So from here we are able to get the values of y1, y2 and y3. Now using these values of y1, y2, y3, we have to find out the values of x1, x2 and x3. Now you see again. So what we have say this. This one. So see, earlier we have used the L. Now we see the equation says LT transpose of T. So L transpose T X is equal to Y. So that means we will be taking the second matrix over here, 5 3 minus 1. So when we take this particular equation, now we have the values of L transpose T. We know the value of Y. So from here we can, using this equation, we can compute the value of X. So what do? We again create the linear equations over here. 5x1 plus 3x2 minus x3. See, multiplying this row, the multiplying first row with the, you can say this x1, x2 and x3. So we get the first equation. Similarly, multiply second row with the x1, x2, x3, we get the second equation, and similarly we get the third equation. So from the third equation we can see 3x3 is equal to 3. So simply we get x3 is equal to 3. So we get the first value of the x. Then we are able to get again, just substituting the value of x3 in the another equation. You can say put it in the second equation. X3 is equal to 1. So we get x2 is equal to, you can say 3 by 3, that is equal to 1. Similarly, putting the values of x1, we have x3 and x2. So putting the value of x2 and x3 in the first equation, we are able to get the value of x1 is equal to 1. So these are the final values of x1, x2, x3. That is the solution we have found for solving the initial linear equations that we have got. So using these three linear equations. So this is called as the Cholesky decomposition method for solving the linear equations. Now you can tell me if you have any doubts. Otherwise, we will take one exercise and do that. So okay, you start doing, then you will come across. Just excuse me. As I told you that Cholesky decomposition is used in the least-square regression. So here you see a linear regression. It takes the form of y is equal to x into beta, where y is the vector, y is the dependent variables. That is the output that we basically try to find out, and x is the vector of independent variables. That means they can be the features on the basis of which we compute the value of y. Let us say you can say you want to predict the price of a house, or you want to predict the price of any shares in for the share market. So in that case, your x are the input values that is you are going to take, and y is the value that you want to predict. So now least square regression basically it refers to finding out the vector b beta where the square differences between the predicted and the actual values so is minimized. So that means whatever will be, so we are trying to predict any value such that it is close to the actual value. So minimize the loss or minimize the error, or you can say maximize the accuracy. And you have to understand why we are studying the Cholesky decomposition and SVD, because they are roughly twice as efficient as other methods for solving the linear equations. So the Cholesky decomposition is, you can say, far better than your LU decomposition, and similarly your SVD is also better than your LU decomposition for solving linear equations. So here you can say where the objective is to minimize the residual sum of squares. So this can be written as minimize the y minus x beta into y minus transpose. So see what we have written, y minus x beta is, that means the actual value and the predicted value, we want to minimize that. So we have taken the dot product of that. So the two vectors, you can say the two matrices that we have used to represent over there, representing matrix A as a product of the lower triangular matrix and the transpose of that. So similarly, we are just converting into a form. Then we take the partial derivative of that. After taking the derivative of that, we are able to get that particular form only, minus 2 of x transpose t into y minus x beta. And we know the, see, when we we create this is equal to 0, we get x transpose of and we multiply that these two on the right hand side parameters. So we are able to get x transpose t of x into beta is equal to x transpose t of y. So that means it looks like what we have studied just now in the Cholesky decomposition, that xt transpose t into x, it looks like it is equal to L transpose of t into L into beta is equal to x transpose of t. So that means using this, see, we have converted into that particular form. So here now we can apply the Cholesky decomposition to solve this particular equation. So now all of you take out your notebooks. So these are the equations that are given to you. Now you compute, apply the Cholesky decomposition in order to find the solutions. So that means to find the values of these variables.